planar graph. What is meant by a planar graph? A graph G is said to be planar if there exists some geometric representation of the graph G which can be drawn on a plane such that no two of its edges intersect. No two of its edges intersect. A graph G is planar if there exists some geometric representation in which any two edges not intersect. A graph that cannot be drawn on a plane without a crossover between its edges is called the non-planar. Okay. A drawing of a geometric representation of a graph on any surface such that no edge intersect is called the embedding. Thus, to declare that a graph G is non-planar, we have to show that all possible geometric representation of G, none can be embedded in a plane. A geometric graph G is planar if there exists a graph isomorphic to G that is embedded in a plane. Otherwise, G is non-planar. A geometric graph G is planar if there exists a graph isometric to G that is embedded in a plane. Otherwise, G is non-planar. An embedding of a planar graph G on a plane is called a plane representation of G. So, in order to check whether a graph is planar, we have to draw that graph in a plane so that no two of its edges are not intersecting. Okay, if any two edges are intersecting, there is no possible embedding. We can say that a graph is non-planar. Now, let us consider this example. Here, we have the edges A, B, C, D, E, F. Now, here you can see that the edge E and F crossover. Okay, crossover the other. So, here we can draw this edge F in this way. That is, in order to avoid the intersection, we have to redraw that edge in this way as in the figure 2. So, we can say that, see that there is no crossover here. So, this graph is a planar graph. This graph is a planar graph now after redrawing. Okay, similarly, here we consider this graph. Here you can see that no edges overlap here. So, this is a planar graph. Actually, this is the planar representation of the cube. Okay. So, this is all about planar and non-planar graph. Now, we can move to the Kuratowski's two graphs. Very important theorem. Now, need to study the proof of Kuratowski's theorem to you. Kuratowski's two graphs. Kuratowski's two graphs are K5 and K33. Both are non-planar. Both are non-planar graph. So, just we can write the statement of the Kuratowski's theorem. There are two theorems. First one, the complete graph of 5 vertices is non-planar. That means K5 is non-planar. That is the first theorem. K5 is non-planar. The proof is simple. Now I am not going to the proof now. If you want, you can refer the textbook. Okay. The second theorem is the Kuratowski's second graph K33 is non-planar. This is Kuratowski's second graph K33, that is non-planar. Okay. Both the graphs are non-planar. These two theorems are known as Kuratowski's theorems. Now, next, what is K5? K5 means the complete graph on 5 vertices. I will draw the graph for you now. The complete graph on 5 vertices. That means any two vertices are connected by an edge. Every two vertices are connected by an edge. Okay, this is our K5. Now what is K33? K33 means the bipartite graph, complete bipartite graph. This is the complete bipartite graph K33. Okay. So, if you try to draw the geometric representation, another geometric representation, you can see that its edges are intersecting. We cannot redraw it without any intersection. Now we can move to the properties common to K5 and K33. Now, properties common to K5 and K33. Okay, first one, both are regular graphs. Both are regular graph. Second property, both are non-planar. Both are non-planar graphs. Now the third one, removal of one edge or a vertex makes each graph a planar graph. Each a planar graph. Fourth one, the Kuratowski's first graph is the non-planar graph with the smallest number of vertices. That means K33 is, the first graph is K5, okay. K5, Kuratowski's first graph K5 is the non-planar graph with the smallest number of vertices. At Kuratowski's second graph, that means K33. K33 is the non-planar graph with the smallest number of edges. Smallest number of edges. Thus, both are simplest non-planar graphs. So, what are the simplest non-planar graph? The simplest non-planar graph are K5 and K33. K5 is the non-planar graph with the smallest number of vertices and K33 is the non-planar graph with the smallest number of edges. These are the properties common to K5 and K33. Now, we can move to the different representation of planar graph. Okay, so you write this heading as different representation of a planar graph. Now, next theorem, theorem 5.3. Note this statement now. Any simple planar graph can be embedded in a plane such that every edge is drawn as a straight line segment. Okay, not this theorem statement. This theorem statement we will use in some other theorem. So you note this statement. Any simple planar graph can be embedded in a plane such that every edge is drawn as a straight line segment. Next, here you simply note the definition. What is meant by a region? Region means a plane representation of a graph that divide the plane into region. That divides the plane into regions. The other names are windows, faces, or meshes. Next, what is meant by an infinite region? Infinite region. The portion of the plane lying outside a graph embedded in a plane is infinite in its extent. Such a region is called infinite, unbounded, outer or exterior regions for that particular plane representation. Now, let us consider one example here. So, here we can mark the vertices as V1, V2, here V3, then V5. Here we can mark V2, join like this. Then there is an edge from V3 to V4, then V5 to V4, then V4 to V2, then V2 to V5. Consider this example. Now, you mark this region. So, simply mark that this region. Okay. Now, actually, that is inside that portion. Now, we can convert that V1, V3, V5 as an infinite region as in the second figure. The same graph can be drawn like this also. So, here this is V1, V2, V4, here V3 and V5. This is another embedding. V1 to okay, so here you can see that V1, V3, V5 now represent the infinite region in the second figure. That means the unbounded region outside V1, V5 and V3. Any region can be made infinite region by proper embedding. So, here we converted the V1, V3, V5 region as an infinite region in the second figure by proper embedding. Okay, so the portion of the plane region that lying outside a graph embedded in a plane is infinite in its extent. Such a region is called the infinite, unbounded, outer, exterior region for that particular plane representation. Okay, next we can move to embedding on a sphere. Embedding on a sphere. In that we have one theorem. Theorem 5.4. A graph can be embedded in the surface of a sphere. A graph can be embedded in the surface of a sphere if and only if it can be embedded in a plane. It can be embedded in a plane. A graph can be embedded in the surface of a sphere. Surface of a sphere if and only if it can be embedded in a plane. Okay. For that, consider a figure like this. Consider this plane. Now we can draw a sphere also here. Now here you mark the south pole as SP and the north pole as NP. This is the north pole and this is the south pole. Now we consider a point P here in the plane. After that we join those 2 points by a straight line. Join this north pole with this point P. Now here we have an intersection point here. Now we can denote that point by P dash. Okay. Now here we are considering the stereographic projection. Stereographic projection. Now here we put the surface. Here we put the sphere on the plane and call the point of contact SP as the south pole. At point SP, draw a straight line perpendicular to the plane and let the point where this line intersects the surface of the sphere be called NP, the north pole. Now, corresponding to any point P on the plane, there exists a unique point P dash on this sphere and vice versa, where P dash is the point at which the straight line from point P to the point NP intersects intersect the surface of the sphere. Thus, there is a one-to-one correspondence between the points of the sphere and the finite points on the plane. And the point at the infinity in positive plane corresponds to the point NP on the positive sphere. Now, from this construction, it is clear that any graph can be embedded in a plane. That can be drawn on a plane such that its edges does not intersect. Okay, so any graph can be embedded in a plane, can also be embedded in the surface of the sphere and vice versa. And this completes the proof of the theorem. Next, we can consider another theorem. The theorem says a planar graph may be embedded in a plane such that any specified region can be made the infinite region. A planar graph may be embedded. This is theorem 5.5. Okay. A planar graph may be embedded in a plane such that any specified region can be made the infinity region according to our choice. Next, we can move to the very important theorem, theorem 5.6. The proof is also important. Okay. Theorem 5.6. A connected planar graph, planar graph with n vertices and e edges has e minus n plus 2 regions. So, in order to calculate the number of regions, you can make use of this theorem. In a connected planar graph, let us note this point. This is a connected planar graph. In the case of a connected planar graph with n vertices, e edges, there are e minus n plus 2 region. Okay, so we have to consider the proof here. The proof is very important for you. Now, it will suffice to prove the theorem for a simple graph, because adding a self loop or a parallel edge simply adds one region to the graph and simultaneously increase the value of e by 1. We can also remove all edges that do not form the boundaries of any region. For example, consider the following graph. So here we can name the edges also here. This is, we can draw one more edge here from 1 to here. Now we can name the edges 1, this is 2, and here this is 3, then we can mark 4, 5, here this one 6, then after that we can name these edges. Here we have this as E, F, here this one, this particular edge, small edge, G. Okay. Now if you want, you can name this one also. That is, here we have an edge, name it as 7. So here in figure you can see that E, F and G are edges that does not form the boundary of any region. So, addition of or removal of any such edge increases or decreases the number of edges by 1 and increases or decreases the number of vertices by 1, keeping the quantity E minus n unaltered. Okay. Since any simple planar graph can have a plane representation such that each edge is a straight line, any planar graph can be drawn such that each region is a polygon. Now, let the polygon representing the given graph consist of F faces. Here we assuming there are F faces. And let KP denote the number of p-sided regions. Here it denote the number of p-sided regions. Okay. Now, in order to get the smallest region, we will have at least the smallest region is given by 3 edges. Okay. So, 3 edges are necessary to have a region. Since each edge is on the boundary of exactly 2 regions, you can see that each edge is on the boundary of exactly 2 regions. Here we will have 3 into K3 plus 4 into K4 etc. plus R into KR is equal to 2 times E. Here KP denotes the number of p-sided regions. So, K3 denotes the number of 3-sided regions. K4 denotes the number of k-sided regions. Now, here actually, if you are considering K3, you will have three edges there. 3 edges. Okay. So, each edge contributes 2 to the number of edges. So, this quantity equal to 2 times E. Take it as equation number 1. Where what is KR? KR denote the, here KR denote the number of polygons with the maximum edges. KR denote the number of polygons with the maximum edges. Okay. Also, here K3 plus K4. Here K3 denoted a region with 3 sides. K4 denote another region with 4 sides. So, what is the total number of regions here? Total number of regions is F. This is the total number of faces. Now, you take this as equation number 2. Okay. Now, the sum of all angles subtended at each vertex in a polygon is 2 pi n. That is an important result. The sum of all angles subtended at each vertex in the polygon is 2 pi n. Take it as equation number 3. Now here, sum of all angles means that the angle include the interior angle and the exterior angle, both angles. Okay, so here we want to remember both the formula here. What is the sum of all interior angles of a p-sided polygon and what is the sum of all exterior angle of a p-sided polygon? So you note that result here. Now I am cleaning this portion now. Just cleaning this much portion. Okay. Now you note this formula. The sum of all interior angles of a p-sided polygon is pi into p minus 2 and the sum of all exterior angles of a p-sided polygon is pi into p plus 2. So we want these two formula. So you note this result. The sum of all interior angles of a p-sided polygon is pi into p minus 2 and the sum of all exterior angle of a p-sided polygon is pi into p plus 2. Okay. Here, from the third formula, the sum of all angles subtended at each vertex in the polygon is 2 pi n. So we can represent this 2 pi n as the sum of the exterior angles and the interior angles. So we can move to that now. So equation number 3 is the grand sum of all interior angles of f minus 1 finite region. There are total number of faces is f. Here each face represents a region. So there are total f minus 1 interior region and 1 exterior region. So equation number 3 is the grand sum of all interior angles of f minus 1 finite region and the sum of the exterior angles of the polygon defining the infinite region. Now we can represent equation 3 in that way. So equation number 3 become, that means equation number 3 represented 2 pi n. So here you assume that there are p boundaries in the exterior region. P boundaries in the exterior region. So the number of finite p-sided region is kp minus 1. kp minus 1. So now the equation number 3 can be represented in this way. 2 pi n is equal to the sum of all interior angles of f minus 1 finite region. So here we will have this sigma I varies from 1, here I varies from 3. So the minimum value of I is 3 to r. Then the formula pi into p minus 2. Here we have I minus 2 into ki. There are ki such interior angles. Then plus pi into p minus 2 into kp minus 1. That corresponds to the, here we are assuming there are p boundaries in the exterior region. Then plus pi into p plus 2. That corresponds to our exterior region. Okay. Now we can add all these things now. Okay. Now this is equal to, now we can expand this. So this is pi into 3 minus 2 into k3 plus pi into 4 minus 2 into k4 plus etc. plus pi into r minus 2 into kr plus pi into p minus 2 into kp minus pi into p minus 2, then pi into p plus 2. Okay. Now that is equal to pi into, here you will have 3k3 plus 4k4 plus etc. plus rkr. Then you grouping the terms here like this. Then minus of k3 plus k4 plus etc. plus kr. Here it is 2 times. Then plus the remaining terms are here. What are the remaining terms here? Pi into here k up to kr, then pi into p minus 2. That means here you can write the term last term. When you are adding these two terms, you will have here minus pi p plus pi p, that is cancelled. Then here pi 2 pi and here what is the total sum here? Final sum plus 4i also. Plus 4 pi. So here we have 8 okay. So here we considering the terms like this. First we grouping the terms. Pi into here we consider the term I not equal to p. Okay. Then after that you will have up to I varies from 1 to r pi into I minus 2 into ki. Then pi into, then here you have minus pi. What is the answer here? This term become Sorry, here I forgot to write this kp minus. Okay, here it is. Kp minus 1 is here. Okay. That is okay. Pi into p minus 2 into kp minus pi into p minus 2. Then minus pi p plus pi p cancelled. After that here we have a 4 pi. Here plus 2 pi. Then here plus 2 pi. That is 4 pi. Now this is pi into now 2, 3, k3 plus 4, k4 plus etc. plus rkr is 2e. So 2e minus, now here we have 2 into k3 plus k4 plus etc. plus kr. That represent our f. That means 2f. Then plus 4f. 4 pi. Okay. So that is equal to, here 2 is common. So 2 pi into e minus f plus 4 pi. Okay, actually this is equal, 2 pi n is equal to this one. Now you can cancel 2 pi throughout. So what is the remaining terms here? So after the cancellation of 2 pi, we will have n is equal to e minus f plus, here 2 pi is cancelled. So n is equal to e minus f plus 2, or f is equal to e minus n plus 2. And this completes the proof of the theorem. Okay. Now let us move to a corollary. Very important result. Corollary. In any simple connected planar graph with f regions, n vertices and e edges where e greater than 2, the following inequalities must hold. What are the inequalities here? Here e greater than or equal to 3 by 2 f and e less than or equal to 3n minus 6. Now we can move to the proof also now. Simple proof. Since each region is bounded by at least 3 edges. Each region is bounded by at least 3 edges and each edge belongs to exactly 2 region. So we must have 2e greater than or equal to 3f. From that we will have e greater than or equal to 3 by 2f. So the first proof is over. Similarly, we have the Euler's formula. The previous theorem is known as the Euler's formula, that is f is equal to e minus n plus 2. This is our Euler's formula. Now we can make use of this Euler formula in this inequality. So e greater than or equal to 3 by 2 into e minus n minus 2. Sorry, here e minus n plus 2. E minus n plus 2. Okay. Now we can solve this. E minus 3 by 2e greater than or equal to minus 3 by 2n plus 3. Okay. Now Now 1 minus 3 by 2, that means minus 1 by 2. So minus e by 2 greater than or equal to minus 3 by 2n plus 3. That means e by 2 less than or equal to 3 by 2n minus 3. That means e less than or equal to 3n minus 6. That is the proof of the second inequality. Now, in order to check whether a graph is planar, we can use the above inequality. E less than or equal to 3n minus 6. This is necessary but not sufficient. Okay. Here, we can consider the example K5. Consider K5. We know K5 is non-planar and it is the first Kurzgesagt graph. Here, we can consider in the case of K5, what is the number of vertices? N is equal to 5. And what is the number of edges? E is equal to 10. Now, here we can calculate 3n minus 6. So, 3n minus 6 is 15 minus 6, that is 9. And now you can compare this with the E. Here, you can see that this value less than E. What is E here? E is equal to 10. Here 3n minus 6 less than 10, less than E. So that is a contradiction to our result. E less than or equal to 3n minus 6. Therefore K5 is non-planar. K5 is non-planar. So in order to, a planar graph always satisfies this result. A planar graph always satisfies this result. Okay. But this result does not imply, if this result is satisfied, that result does not imply the graph is planar. For example, you consider K33. Consider K33. Here, what is the number of edges? Number of edges is 9 and the number of vertices is 6. Now you consider 3n minus 6. 3n minus 6 is equal to 18 minus 6 is equal to 12. Okay, here number of edges is 9. So 9 equal to E, which is less than or equal to 3n minus 6 is equal to 12. That means 9 less than 12. The condition is satisfied, but we know the Kurzgesagt's second graph is non-planar. Non-planar. So this condition satisfied does not imply the graph is planar. So if a graph is planar, then this result is satisfied. That's all. Now, every region is bounded with a, we can consider K33 also. Yeah, wait. Now we consider another proof here. Consider K33. K33 is the Kurzgesagt graph, second graph. Actually, this is our complete bipartite graph on graph like this. Okay, now we can mark the edges also. Now you mark the edges here to here, then edge here to here, then edge here to here. Now one edge cannot draw. We can't draw the one edge here. So here now we can move to the proof now. Every edge is bounded with, in the case of K33, every edge is bounded with 4 edges. Every edge is bounded with 4 edges. Therefore, 2E greater than or equal to 4F. That means 2E greater than or equal to 4 into. Now we can make use of Euler's theorem. F is equal to E minus n plus 2. That means 4n greater than or equal to 2E plus 8. That is 2E less than or equal to 4n minus 8. that is E less than or equal to 2n minus 4. Okay, so here we have 9 less than or equal to 12 minus 4, that is equal to 8, and which is a contradiction, and so K33 is non-planar. Okay, so these are very important problems for you to prove K5 is non-planar, K33 is non-planar. Using this inequality, it is very easy. Okay, now let us stop now. Thank you all.